Yeah, so first the question, who is here from particle physics? Good. So I'll start with a story. A couple of years ago, I had a flight layover at this big international airport where I met this lady, a well-educated, mid-aged lady who asked me what I do. I said I study experimental particle physics, and she was like, what is that? I anticipated a long discussion, so I asked her whether she's ever heard of the Large Hadron Collider or maybe Higgs boson. She sighed disappointedly and asked me, you're those guys that we give big bucks so you would tell us that God didn't create the universe in 7 days? My short answer was not only. My long answer took us 3 hours of the layover that we had. This question that this lady asked me is a popular question in a society, and I would like to use these 10 minutes today to tell you how we study elementary particles and, more importantly, why we do it. And of course, I have to start with a theory. Since the beginning of our days, we wanted to know what we and the universe around us is made of, how it all started. And if we zoom in on the smallest parts of our body or any object around us, like a hair, and we keep on zooming in, we come to a point when we can visualize some really microstructures and even molecules. And then even if we go down, we know that molecules are made out of atoms, and atoms are made out of electrons and nuclei. That is far, far smaller than the atom itself. Physicists didn't stop here. We learned that the atoms are made out of protons and neutrons, and we didn't even stop here, and we learned that the protons and neutrons are made out of quarks. So all this was put in a beautiful theory that is called the Standard Model of Particle Physics, and it looks like this. Or better, it looks like this. So basically, the theory gave us this picture of elementary particles, of these building blocks of the universe, and explained how it is all held together. Now the question is how the hell we studied what I showed you. For this, we build huge machines that we call accelerators, colliders, and detectors. And the most known experimental particle physics project is the Large Hadron Collider, which is this 27 kilometer circular pipe where we accelerate particles to almost the speed of light. And then in 4 collision points at the collider, we smash them one into another. And here I'm showing a little animation. So this is accelerator particles. In the collision point, it meets another particle, and the energy, because we accelerate it so fast, the energy that these particles have is enormous, and then in the collision point, it's double of that energy. So once the collision happened, we study the products of the collision. And this is a beautiful event, an example of a good event that we selected from all the data. It's a Z boson decay to 2 muons. You don't need to know what it is, but just to say. The question is, okay, this is one event that we selected. The collisions are happening at the rate of 40 million collisions per second, so you can imagine the amount of data. It's enormous. The question is how we measure it, how we catch these products of the collision. For this, we built a detector, what we call a detector. It's this huge machine that you can see all the dimensions that I put on the slide. This is an example of one of the 4 experiments at the LHC. It's called Atlas. It has thousands of participants. It was built by the effort of thousands of people, and Israeli institutions took a valuable part in it. And this whole system consists of subsystems, detectors that are smaller and are of different types and shapes and sizes in order to measure certain types of particles. And this is, again, just to impress you with the scale. here, this is the outer part of the Atlas experiment, and actually the detector planes that you can see here, part of them was built actually here at Weizmann. So what I showed you so far is beautiful. The experiments are running for more than 10 years now. We know how to measure things. We do it for more than 10 years. We discovered the Higgs boson. Beautiful. The problem is that this is not everything. We still don't know what is gravity. We don't understand where more than 95% of the mass of the universe comes from. We don't understand why there is so less of antimatter in the nature. So what we think we can do, we can build even larger machine. Yes. This is one of the proposed projects. It's not built. We don't know if it's ever going to be built, but this is it. If it's going to be built, it's going to be like almost 4 times larger than the Large Hadron Collider. And this machine is going to be even more powerful. The energy is going to be even higher. The rate of the collisions will be higher, so we need better detectors, advanced detectors. And here we come to a part of the research that I do for my degree. So what I do, what our lab does, we develop detectors that can be used in this particular part of the big detector that is called calorimeter. Calorimeter is responsible for measuring energy of the particles, and it is highlighted here in the blue. So the requirements that we have for the calorimeter is the good granularity segmentation, so we will have a good resolution. Of course, the calorimeter that we are going to build it has to be efficient, so we will not miss any important data. And it has to be reliable in terms of stability, uniformity, and so on and so forth. So the idea is to build what we call sampling calorimeter, where we will alternate layers of absorber and the sensitive detector plane. And so this will be our Z segmentation, and then each plane will be also segmented in XY. So we will have 3D segmentation. And here, this is example of one technological prototype that was already built and tested. It's still very small. But yeah, this is the idea. What I do for my degree, I try to design and develop a single sampling element, so single plane that is going to be like put in stack. And the technology is based on gaseous detectors technology. Again, you don't need to know what it is. So it works on the principle of gas ionization of the gas. So we have, as an active media inside the detector, we have gas. And when the charged particle, ionizing particle passes through, it creates negative and positive charge. And then we multiply this charge in this microstructure, these tiny holes, to get actually a good signal. Simple idea, you can say. The detector proved to be efficient. It can be scalable. So what I do for my degree, I scale up. And how it goes, so the concept was proved years ago. What we do now, we design and assemble larger scale prototypes. So the largest we got is 50 by 50 centimeters. Then we, of course, test our detectors in the lab at the test beam facility. Then we characterize it, so we analyze the data. Here you can see the efficiency map of our prototype, so it's almost 100% efficient. We also assess the uniformity, and we measure many other things. Then we, based on the characterization, based on the performance of the actual, since it has to be scientific, so I put plots. So here you can see, like it doesn't stop on here. We don't just characterize, we also do the simulation. So based on the data that we have, we build this simulation model of a full prototype. And then using the simulated data, we can actually measure the energy and estimate what resolution we have. So how good we can be for future collider experiment, if we can. And yeah, so that's about very briefly, very simplified about my research. But so far, I never told you why we do all this. And every time I ask this question, I feel confronted because it's really a lot of effort, it's a lot of money, and people don't understand why. So the first reason is, of course, scientific curiosity. As I said before, we want to learn the nature, we want to know where it all started, how it all started, why it is like this now, how it will be in the future. This is, I think we are here all more or less curious about it. The second, reason, and here I would like to make an accent because I like this part. I'm working on hardware, I like this part. The research that we do is impactful on many fields. It's not a direct application, but it is still an application. And here I will give you some examples. The first that comes to mind is radiation therapy and medical imaging. The accelerator technologies are used in proton therapy, for example. Thousands of hospitals around the world have small accelerators to cure cancer with protons or even electrons. And the detector technologies are used in medical imaging. So all the CT scans, PET scans, they can employ our technologies, and they actually do. The second application is a homeland security. So the large-scale detectors can be actually used to examine big objects like trucks, containers, and ships at the borders. Another application is power transmission. So in accelerator, we use these magnets to accelerate the particles. And the superconductive materials that we use, they can be used for power transmission, which will make it faster and more efficient. Another application is data storage and analysis. I told you how many collisions, how many data we have, how much data we have. The technologies that we use to store this data and analyze this data can be used and actually already used in banking, finance, anywhere where you have big data. Okay. Another reason why we should do particle physics is science teaching. Our community, CERN in particular, has lots of programs for high school students, undergrad students, which really encourages young generation to be involved and to be actually excited about science. I think it's important. And the last reason I want to highlight is this field is a great way to unite nations. Again, particle physics community is tens of thousands of people. And at CERN, we are working together, not only at CERN, in many national labs in the States or in these big collaborations. We work as a whole for this major joint goal. And I think it's the greatest diplomatic success. Here I'll stop, and if you have questions, I'll be glad answering them. Thank you.